Today I want to talk a little bit about a scientist by the name of Jacques Charles. His name is actually something like Jacques Alexander Caesar Charles. It's like the most ridiculously regal sounding name ever. He's a French chemist or physicist. You know, chemistry and physics back then, there's a lot of overlap. There still is a lot of overlap, and I always am claiming physicists as chemists. But Jacques Charles was studying gases. And if you Google Jacques Charles, which I highly recommend doing, he's known as like a daring hot air balloonist because back in that time, so I have his years here, back in the day, the people that were studying gases were looking at the new cool technology that you could do with them in the same way that a lot of scientists do today. You know, we really study something and then we find all the cool tech and then we play with the cool tech, and it's kind of all part of the experience, I think. So he was a hot air balloonist and he had some hot air ballooning adventures, and the story goes that he was kind of like got in his hot air balloon. And just keep in mind, like back in these days, it's like a balloon that's tied off and then lashed to kind of like some sort of, if you look at pictures of it, it kind of looks like a sleigh almost, which is kind of festive. So it's like lashed to a sleigh. It's like in there, the balloon is knotted off, and then there's some sort of, you know, flame under it, which is all well and good. That's kind of how it works these days too, except for back in that day, the hot air in the balloon was hydrogen, which, if you've heard of something called the Hindenburg, then you know how dangerous that could possibly be. So he had a hydrogen hot air balloon, which just sounds like a terrible idea. But the story goes that he was up over the French countryside. You know, I think he flew out of Paris or somewhere, one of the bigger cities, you know, and you know, the academics of the day, people had seen hot air balloons before, but you get out over the countryside and they'd never seen a hot air balloon before, and so they thought it was some sort of sky demon, and they threw rocks and pitchforks and sticks, and they pulled the balloon down, and it was all sorts of scary. There's another story, and I don't know if this is the same run or a different run, where because there's no like let out the air valve, it's all closed off, so he just shot up like super far into the atmosphere and got really, really high in terms of altitude. And it was kind of a scary experience as well. So he's kind of known as an adventurer and a daring balloonist, which I just think is kind of a fun designation. But we in the chemistry world know Jacques Charles because of his work with the study of volume and temperature in gases. And the reason I talk about the hot air ballooning story is that I think that it'll help to remind you of what his law is, because Charles' law is the relationship between the volume and the temperature of gas when we keep the pressure and the number of particles of gas constant. And what he found is that there's a direct relationship, that the volume is directly proportional to the temperature of the gas. So if I have a balloon here, you know, the balloon is flexible, but it's tied off, so I'm not allowing any new gas particles in or out. I'm going to keep the internal and external pressures as constant as possible. It has some sort of initial volume, and let's just say whatever the initial temperature is. Now if I heat up this balloon, so here's my flame, and I'm going to increase the temperature here, then that's going to increase the volume of my balloon. And I'm going to keep the same number of gas particles. They've just moved around more. They've just spread out a little bit more. Right, because they're moving around faster because you increase the temperature, and per kinetic molecular theory, when you increase the temperature, you increase the speed and motion of particles. So you increased the temperature, you have some sort of new temperature down here, and that gives you an increased volume. So there's this direct proportionality. When you increase the volume, you increase, or when you increase the temperature, you increase the volume, or vice versa, really. I mean, it's a direct relationship either way. We usually think about it in the opposite, that you increase the temperature, you increase the volume. You might have experienced this if you've ever got a helium balloon from a grocery store or a party store, and you go into the store and you go get your helium balloon and they fill it up in the store, and then you go out and it's like winter time or colder outside, and then you look at your balloon and it looks kind of shriveled up. And so you get all mad and you go into the store and you're going to demand that they fill it with more helium, but when you go back in, then it expands back outward again, right? So there's that increased volume with an increase in temperature, or vice versa. When you take that temperature away, when you cool things down, then the volume decreases. Another fun thing to do is to blow up a balloon and then knot it off and stick it in the freezer and then see what happens, because then the temperature goes down, your volume we would expect to go down. Maybe you don't think that's fun. I think that's a delightful way to spend a weekend. So with a direct relationship or direct proportionality, if I have the ratio of the variables, so the volume over the temperature, that's going to give me some sort of constant. And then when I change up one of the variables, so if I change the temperature, that gives me a new volume. That ratio, though, stays the same. So the ratio of the values for that particular system are equal to a constant, and therefore I can set the ratios equal to each other. And we call this V1 over T1 is equal to V2 over T2. This is Charles' law, named after Jacques Charles and his daring balloon adventures. So we can use it to solve problems that look like this. So we have some sort of helium balloon. Let's say that it's slightly underfilled. We have it at room temperature, which let's call that 24 degrees Celsius. Here's my underfilled volume of 3.9 liters. So when I increase the temperature to 55 degrees Celsius, what is the new volume? There's some assumptions that are built into this, that I'm not changing the number of moles, so I'm not adding or taking away any of the moles of gas. And also that I'm not messing with the pressure in any sort of significant way. So we're going to use our Charles law here. And I like to solve these problems by listing out the variables that were given and then figure out what I'm solving for. So my initial temperature is 24 degrees Celsius. My initial volume is 3.9 liters. I'm changing the temperature, so I have a new T, which is now 55 degrees Celsius, and it's asking me for the new volume of gas. Now, a couple things about gas law problems. With gas laws in general, you have to convert your temperatures to Kelvin. You need the absolute temperature when you're talking about these ratios. So even though your temperature units stay the same, it's important to still convert to Kelvin for all of these, otherwise you will get the ratios incorrect. And this is going to play more of a role when we get into the ideal gas law in later videos, but it's good practice and is required for the correct answers in these types of problems to convert to our Kelvin. So our magic number for Kelvin is 273.15. I'm going to be rounding to a ones place though, because I'm adding. So when I do that, I end up with 297 Kelvin. And then 55 here, 273.15 again is my magic number. I'm rounding to the ones place because I'm adding for sig figs. So that gives me 328, Kelvin. Now, in general, it's good practice to just leave as many significant figures or leave as much precision as you can and then round at the end. So you could do that as well. I'm only working with 2 sig figs though, overall. So even with these rounded to the ones place here, it's not going to make a significant difference in this particular one, but just as a side note. Okay, so I'm solving for V2. So to rearrange this thing to solve for V2, then that gives me V1 times T2 over T1 is V2. And now if I kind of plug and chug, then I end up with my 297 times my T2. Sorry, that's what I get for getting overexcited. So my V1, which is 3.9 liters, times my T2, which is 328 Kelvin. All that divided by my 297. Apologies on that. Okay, now when I run this through, then I'm gonna look at my units first. So our Kelvin will divide out and I'll be left with an answer in liters, which is good because I'm solving for a volume, so that setup looks pretty legit. And now if I'm thinking significant figures, which I always am, then I'm going to be rounding my answer to 2 because I'm going to be limited by my volume. And at this point now we are multiplying and dividing. And the other thing I like to keep in mind with these types of problems are How is this going to compare to my initial volume? So is my volume going to be larger or smaller? So I like to have an expectation of what the number is going to be before I put it into my calculator, because my calculator can lie to me. So let's think about this. If I'm increasing the temperature, we know there's a direct relationship between these two. So I should expect an increase in my volume as well. So I'm expecting this to be two significant figures, a positive number, of course, and that positive number is going to be larger than 3.9 liters. And when I plug and chug through here, I end up with 4.3 liters, and that looks good to me. So that's Charles' law. Pretty straightforward, direct relationship, direct proportionality, and a fairly intuitive gas law, which I think is kind of a nice feature. As always, if you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.